So yeah, like I said, I'm with Chance Maritime Technologies. So we're right here in Lafayette, Louisiana. So we're not far, just by Collie Saloon there. We've got a big warehouse, offices, everything like that, different vehicles you can see, um, just locally here and building boats and everything. So we're kind of a startup company. We were established just last year. Right now, we've got a grand total of count them, 5 employees. So, really exciting time to be here, as well as some other support from other groups. So I want to talk a little bit about what are USVs, because not everybody may be super familiar with them. I think everyone knows a lot about autonomous cars. You hear about, Cruise and Waymo and all of those, and not a whole lot of discussion about autonomous boats. So as you might imagine, an autonomous boat or an autonomous ship, generally will have no provision for crew whatsoever. So what you're looking at is a rendering of a, approximately 20-foot long hull, or 6-meter long hull. Typically you've got a suite of different sensors on board, just like you would with any other robot. So for this kind of vehicle, you've got your perception systems usually consist of a marine radar. You'll have visual cameras and infrared cameras. So what you call EO, IR, right? Electro-optical, infrared, and automatic identification system, or AIS. So that one's kind of unique to the marine industry. All boats, or I should say all ships, will generally have an AIS system. I don't know if you guys have ever looked at those maps of the airplanes. You can see all the airplanes flying across, Europe and everything like that, and they've got them all tracked. They've got the same thing for ships, and you can actually go to marinetraffic.com and you can see where all the ships are going. So unfortunately, that only works for big ships. It doesn't work for small ships, and there's also some people will do funny things, like they'll spoof where they're located and things like that because they're trying to export Russian oil or something like that. So you gotta be wary of that one. Not necessarily a trustworthy source. So then localization problem. So of course you've got GPS on board, just like any other vehicle, and then you'll usually have some kind of inertial navigation system to enhance the accuracy. So thing you have to remember, your cell phone, you've got GPS on the cell phone, you think, okay, I can drive a robot or whatever. But the accuracy of that, you've actually got meters of error. And in a lot of cases, you need sub-meter position accuracy to do the job that you're going to do out there. So that gets supplemented with all kinds of different technologies. Communications is the other big area. So you'll have a combination of line of sight and beyond line of sight radios. So line of sight is just what you think, less than 12 miles away, radio system that's point to point. And that could be everything from as simple as Wi-Fi for close range, and then more complicated mesh radios, over different bands. And then beyond line of sight, you've got satellite communication. When I talk about constrained communication, this is really constrained. So you're kind of in a tough situation. The only thing that our saving grace right now is that Starlink seems to be coming together pretty well. We've got a unit that's getting a little more bandwidth than you would with Iridium or something like that. So, and then that's not to mention all the other mechanical systems. So what you call your whole mechanical electrical. So on board your vessel, you've got, your engines and everything. And you think, okay, yeah, I've just got an engine. I drive the boat with the engine. But, if anyone here mechanically minded or marine engineering, something like that. Yeah. So, of course, it's not just an engine, it's all the systems that support the engine. So you've got to have fuel tanks, and you've got to have coolant systems, and those might bring in raw water, seawater, or they might bring in, heat exchangers and all these kind of things. So there's a lot of machinery that you have to manage. And you'll see later in the brief, you can get a lot bigger with these ships. And the bigger the ship, the more systems, the more complicated they are. And there's nobody on board to turn a wrench, So how do you solve that? How do you deal with that? What's the reliability? Those are all big topic areas. And then finally, you've got the payload equipment. So everything above that line was for a boat. That's just to drive a boat around. But it says nothing about the payload. And this is really critical because nobody cares about the boat. No one actually cares about the boat. They care about the job that's being done. They care about collecting data. So it's how am I going to get my data? They don't care about how is the boat driving around, and how's my communication link? These are all auxiliary things, problems we have to solve just so that we can collect the data that we want to collect. So just talk a little comparison here. Again, autonomous cars, which people might be more familiar with, versus autonomous boats, what those look like. Car, you got one mission. What's your mission? I get from this address to that address. That's it. I'm driving from here to there. So yeah, I've got to dodge vehicles along the way, and I got to figure out my lane, figure out my route, whatever. But that's the only mission that you're ever going to do in a car, generally speaking. With a boat, it's multi-mission. I'm going to go through those missions in a minute here, but aside from transportation, where it's like I've got a big shipping container going from A to B, for the most part, you're putting the boat out there to do some job, to do some work. You're surveying an area, you're collecting some data, whether it's for scientific purposes or for commercial purposes or for defense purposes. You're doing something out there. And that means more behaviors, that means more tasks, that means more autonomy, that you have to manage those things. In terms of endurance, a car, it's a day trip. How far are you really going to go, right? It only has to last a day, or to the next gas station or something like that. For a boat, it gets weird. People want a day, they want 7 days, they want 30 days, they want to run as long as they can. They're going to want to run for 100 days, 365 days. And they've got vessels out there that can do that with limitations. There's going to be a big asterisk there. I'll go through that in a minute. But that brings a lot of problems, because again, we get back to the situation of, I've got a boat, I've got engines, and I've got nobody on board to turn a wrench. So, nobody on board to change the oil, right? How often do you have to change oil in a car, So now think about how far a boat's traveling over the course of 100 days or something like that. We've got to manage that some other way. Perception and navigation. So in terms of a car, you're really looking at a 1 minute time horizon. I'm talking about forward through time, projecting forward through time. How far ahead do you have to really think about, where this car is coming, from this intersection or whatever, right? It's only a few, seconds, to a minute that you're really thinking ahead. And in terms of distance, 100 meters around you. I mean, how far ahead do you really have to consider the other cars around you, that it's in your immediate neighborhood, versus if I'm on a boat, the scale is completely different. We have to consider things that are, 30 minutes out, that are, 10 kilometers out, 20 kilometers out. The biggest thing when it comes to collision avoidance with a boat, it's less about dodging, an obstacle, and more about mitigating that situation from ever happening to begin with. You want to have as wide of a berth of whatever you're going to be interacting with further in the future. So that means longer prediction times, longer time horizons, and more predictable action as well in terms of your autonomy. Then comms, so communication systems. So with your car, again, you've got readily available communications. You've got 4G or 5G or what have you. Municipal Wi-Fi or whatever. It's all there. Comms on a boat are difficult. You're depending on satellite systems. There's some offshore 4G, but that's only really near coastal. It's only in certain areas. We're fortunate off the Gulf of Mexico. There's actually pretty good 4G coverage because of all the oil rigs. Every single oil rig has a 4G antenna on it, but that only goes so far. That doesn't go into deep water. And then environmental conditions. So of course cars, rain, sleet, and snow. Well, boats, you got the same stuff, but you've also got the wave dynamics. You've got this interface between two fluid mediums that causes havoc. And when you're really far offshore, you're looking at waves that'll be bigger than a house sometimes. I mean, it's rough out there. Trust me, I've been there. I've been seasick out there. It's bad. So and the boat has to survive it. So anyway, boats are way cooler. That's I might be biased, but there's just interesting problems associated with them. So what do these boats do? So one of the main missions, in terms of, hey, what data do we collect, is hydrographic survey. So this is a big market for uncrewed systems. I would say this is probably one of the most mature markets for uncrewed boats out there. And what you look at on the right side here, This is the kind of standard setup of this would be a crewed boat. So this is a naval oceanographic boat. But the mission is to map the ocean floor, and there's a lot of different ways you can do that. So you see they've got multi-beam echo sounder. So multi-beam is you guys know what a LiDAR is? Something so it's kind of like a LiDAR except with acoustics, and the resolutions are way worse, but it works through the water because LiDAR doesn't really work through the water. So that's cool. And but you're basically trying to find a point here and figure out what its global position is ultimately. So you're trying to coordinate between your GPS, high accuracy GPS, and then all the lever arm calculations to here, and then down to this point, that you get from a sound signal return to go, okay, that's where that point is, and then you generate, you can ultimately generate a map from that after you clean everything up and all. So this is the problem, and it also gets strange because it's not enough to just buy the LiDAR, so to speak. LiDAR, you put it on a car, and the laser is traveling through air and it's going through the speed of light, and that's not really perturbed by anything, right? So we always know how long it's going to take to get the return, right? Easy. Now, what about when you do that in the water? What's the speed of sound through water? It depends, right? So it depends on the temperature of the water. It depends on the salinity of the water. And guess what? That is not the same at every depth. So the speed of sound is changing as that echo is going down, right? And coming back up. And so you have to actually profile with what's called a CTD. And here they're calling a sound velocity profiler, but it's conductivity, temperature, and depth. And you're measuring the conductivity and temperature at every single depth in the water, and back up again. And then you've got a profile of how that changes so that you can do corrections, because all is how long it took to get your sound return back. And you can do corrections and then ultimately figure out where that point is. All right. So that's hydrography in kind of a nutshell. And we're not even talking about hydrography. We're talking about robotic boats. But all of those problems, which are big, annoying problems, have to be put onto a boat. And you can see that it puts, you've got winches and cable management. And, oh, hey, guess what? I don't want to drive backwards into this and foul my prop because I just ran over my my winch cable, that's for my sound profiler. So it kind of, and where is this thing even, and well, the currents are kind of pushing it back and forth, and I'm driving this way, and and what are the currents right now? What are the environmental situations? So then what's the layback of the cable? Where is it sitting? These are all kind of strange problems that add to the complexity of running a boat. And then you'll also see there's other kinds of sensors, side scans. So that's another like a towed sensor. So it's a similar story. You're towing this thing behind you, however far back, and driving through the water and managing that and towing it back up, and when did I pull it out of the water, and how heavy is it, all that stuff. So anyway, it's a lot of interesting problems there. And despite all of these challenges, this, like I said, is the most mature, market for uncrewed stuff. So, and how big of a problem is this? So this is a map of everything that's unmapped in U.S. coastal oceans. So this is territorial waters of the U.S. And all the red is stuff that has not been mapped. That's a lot. It's just a lot. And, you might see there's also these like seabed 2040, like, hey, we're going to map the entire ocean by then. So that's even more, right? And you'll notice there's some patterns here of, well, we did pretty good at mapping, areas really close to the land, and we did pretty good at, mapping everywhere that there might be an oil field, and oh, look at that, Florida doesn't allow any offshore oil and gas, and so because of that, nobody's bothered to map anything, because why would you? And then similarly over here, oh, but there's shipping lanes over, by Los Angeles or San Diego or whatever, and so we've mapped that pretty well. So you could kind of see the patterns of why there's things like, and then, oh, all of Alaska is just, totally unmapped, because who was driving up there? Because it's all ice, and now it's not ice anymore. So we need to figure that out, right? So this is a big problem, and really the bottom line is, in order to map all of this data, you need uncrewed systems. It's impossible to do it with crewed vehicles, just because you just can't collect that much data. The only way to get the volume. So there's other industries though too. Marine construction is another area. So anytime you're going to put something offshore, that thing needs to be positioned. But oh, by the way, it's not just the thing you're putting out there. It's not just the offshore wind platform. It's not just the oil rig. Somehow you've got to get those resources back to shore. So if I'm putting an offshore wind turbine, and there's a lot of those, I've still got to run a cable that comes back, a power cable that comes back. Or if I'm putting an oil platform offshore, well, guess what? I got to run an oil pipeline back. And if you ever look at there's a great map you can get, and it shows you all of the pipelines, because it's all public information. You can see all the pipelines that are scattered over the Gulf of Mexico, and you're going to have your mind blown with how many there are. And it's not just that. You lay the pipeline, and then what? You got to inspect it. We can't have oil leaks. We can't have Deepwater Horizon happening again. So how do you inspect it? And guess what? They move. They're like spaghetti noodles in the Gulf. They move around constantly, and they get buried. They get buried under the sand. So another big problem, right? So inspections are big. Every one of these wind turbines, you might need to look at geotechnical properties of the area that it's being moored at. You might have to look at, and these are floating ones, but probably the ones in the Gulf are going to be fixed platforms, not floating, because we're shallow enough. But off the Pacific, they're going to be all floating, So, but you still got moorings, so there's geotechnical problems, and you gotta look at all that, right? And then there's metrology and biological site surveys. So BOEM, who is the regulatory body that says, regulates all offshore energy management. It's the Bureau of Offshore Energy Management. I think that's the right one. So they say, hey, you can't just go and build a platform here or a wind turbine here, because how are you affecting the environment? Is there a reef there? Is there an ancient archaeological site that's there? You remember the water levels used to be a lot lower. There were ancient riverbeds. There's places, especially off the coast of Louisiana, that have gone underwater over the last 50 years, but are covering up archaeological sites, and so they don't want those disturbed, right? So you've got to do site surveys, and so that might be sitting out there for a long time, looking at what fish go by, what birds go by. That'll be what are the currents that are encountered by that area, because that will drive the engineering of your platform, right? So lots and lots of data that needs to be collected in advance of even building the things, and then where you're going to build them, and then where all the the interconnects are going to be laid, and you're not running a pipeline through an oyster reef or something like that, and then maintaining all of that. So big topics there. And then there's defense. So this is the other big market that's out there. You'll see a lot for mine countermeasures or maritime domain awareness. I'm not going to get too deep into this, but I do want to say, just note of interest, this may surprise you all, but all of these boats here were built on the Gulf Coast, and most of them in Louisiana. So, I said probably surprising, but these are all autonomous boats, and they're all built right along here. So, cool stuff. So how do you actually operate these? So one of the most common ways that you operate an uncrewed boat is over line of sight, command and control. And you'll either kind of do this leader follower, kind of force multiplication type of job, where you've got a mothership that drives along, and you can see it's mapping out, it's collecting the swath. So you've got your multi-beams going down, and you're collecting so much data, cone of data as you drive along. And in order to survey an entire area, you've got to do this grid of driving back and forth, and we love to call that as mowing the lawn. It's just like mowing your lawn. You're just going back and forth until you cover all the lawn. That's the only way to collect all the data. Yes.
Both of those still be uncrewed.
Well, so in this particular scenario, the ASV is the only uncrewed, so it's the autonomous surface vehicle, and then the mothership is crewed. So this is with a force multiplication type of job. You've got a traditional crewed ship, and that might be 100 or 200 foot long boat. And then you'll have an uncrewed boat on top. You drop it off the side, and then you just mow the lawn in parallel. So 2 lawnmowers is better than 1. And, why not 3? Why not 4? You can have more lawnmowers as long as you can fit them all on the back of your ship, which, space is a premium. So, and this can and absolutely does increase operational efficiency. So you can get, 40, 50% more efficient. In other words, you're collecting twice as much data. They are able to collect data at the same rate. So this has been kind of proven over and over again. And in fact, a lot of data, I didn't mention it earlier, but this section right here was collected purely with an uncrewed vessel. And part of why this was special was that this particular area, you can see the red is where it gets really shallow. And the only way to get in there was with a smaller little ASV that could, nudge into the to that region and collect the data. So, so that's another advantage. But, wouldn't it be better if I could send that boat out further away from me and, have it collect in some totally different area? And so that's where you start saying over the horizon force multiplication or over the horizon operation of those vessels. So, greater than 12 kilometers. So I can't hit it with a line of sight radio. I've got to use satellite communications to speak with it. And there may not even be a mothership. This might just be on shore. I might want to sit at home drinking my cup of coffee and controlling the ASV over Zoom. Why not, right? It's the it's the same kind of thing. So what's great about this is you can, I said you can deploy more of these ASVs. They don't necessarily have to come off the mothership. You can have them all kind of out there coding a different area. Well, what's challenging about this, though, is that your comms are worse. So how do I even get the data back? We're talking about extremely high density data here that's being collected by every one of these vehicles. Terabytes and terabytes of data. And when you've got a communication link that might be 100 kilobits, per second, which is awful. I don't know how many you guys familiar with dial-up? Did you guys use dial-up before? Anyone? Yeah. Okay. We got some dial-up users. Good. You remember the pain? I guarantee you any dial-up user can still recite the exact tonal code, of dialing up because you eagerly tried to log into AIM. I'm dating myself. That's fine. But you're going back to those kind of times because there's just not good communications. So how do you do over the horizon? So there's a couple different ways to do it. One big approach is with these low power vehicles because they want to run for a really long time. And why do you want to run for a really long time? Well, aside from the fact that there's a big area to cover and you got to collect a lot of data, that area might be really far from a port. So you might have to travel, hundreds of miles to get there. And if you're only driving at, 12 knots or something like that, because most boats are not going as fast. It's not like you're driving 60 miles an hour. You're driving like 10 miles an hour or 15 miles an hour. So you've got a long transit, so you can't just go back and refuel. And obviously there's no gas stations out there. So you want to be able to get really far out there and stay out there for a long time before you come back. So some people have gone, okay, well, I'm going to, use the waves, like Liquid Robotics did, or I'm going to use the wind like Sail Drone. And that way I can get out there and I can, stay forever. And people use the wind. The sailboats would, transit between Europe and the US, and they would take them months, and they made it fine. So we can use these. And they do a great job in the sense that they can run for a really long time. The sail drones, they've run those for a year. But hey, a little secret, what they won't tell you. So the sail drone they had out there for a year, it went from, the Gulf of Mexico, it went all the way down to Africa, and then it came back, which is an extraordinary achievement. About halfway through, they had a boat that came up alongside it, and a diver came off, and the diver went under the boat, and he scraped all the biofouling off the bottom of the boat. You've got barnacles and seaweed and all this stuff that starts growing on the boat because the boat wasn't moving anywhere, and so they needed to clean the hull so that it could drive again. So not really a year, but we'll still give them credit because it's still an outstanding achievement of reliability and everything. But they've got some other problems, and that's power capacity. So power capacity on one of these boats, you're probably looking at 100 watts, 200 watts, and you start looking at, well, what is your computer? Bet your computer power supply there is, 90 watts at least, right? For your laptop, desktop at home might be, you might have a 900 watt power supply in your desktop. So, try running your, big machine learning algorithm on that, or try running, hey, you've got that sonar again. I need kilowatts. I need real power to be able to run that equipment. I've got a sound source that's trying to ping down, hundreds of meters of depth or thousands of meters of depth. So that's limited. So that means that they're kind of limited in mission capability. So to things like metrology, which is just, hey, I'm just going to go out there and I'm going to look at the speed of the wind, the direction of the wind. I'm going to look at the way the currents are going. You might do some biology, chlorophyll fluorometers, things like that. You kind of figure out how much algae there is floating around. And you could do extremely low resolution hydrography. So you just kind of ping every once in a while, but you can't really get a good map. You just kind of, at least a sense of the depth in some areas. And then surveillance. But even then, a lot of these, they're worried about how long they can run a camera for. So they might only take one picture every, 2 minutes or something like that. It's not full length video. And, needless to say, you can't even get it all back because now you're using the comms that these have is even worse than dial-up. Iridium shortburst data is about equivalent to a text message every 15 minutes. So how much information can you jam in a text message every 15 minutes?
So solar panels?
Yep. Yeah. I mean, your solar panels, you think about it, you go on Amazon, look at a solar panel, right? It's about, you'll get a panel that big and it'll be about 200 watts. But, you still got to drive the boat, so you've got to run the propulsion system, if you've got a propulsion system, or you've got to move the rudder. And then you've got to have a computer on there that's running, and you've got to have what we call the hotel loads. So the hotel loads is everything that's on there that's running when you turn on the boat, and that has nothing to do with the payload other than the fact that it's a support system. Yep.
So then does that 200 watts count? Like, is that the average, or is that including peaks?
It's just somewhere in there. I'm just giving a ballpark number. So and it'll depend on the vehicle. Some of the vehicles will be a little bit longer, some will be shorter. I mean, you're talking about boats that are in the range of, I'd say, one of these liquid robotics surfboards, they're about yay big. Some of the sail drones are way longer, they could probably fill up the room. So it'll, again, depend on how many panels they've got and everything. So then the other problem is where you can drive. So remember when I said before about, hey, we got to mow the lawn, right? So you're going back and forth on this grid. Well, which way is the wind pointing? And that matters a lot. Obviously, if you're driving by wind, and you can't drive right into the wind. And then these are also a little funny. Unlike a normal sailboat, you can't really go directly downwind. Anyone sail here? No sailors? Okay. So when you sail, and you're in a normal sailboat, you let out the mainsail and the wind carries you forward, and you can go the fastest when you're going downwind or with the wind, right? When you've got a fixed wing like this, you can't just turn it broadside and then head downstream. It doesn't work like that. These actually work more like airplane wings. So you've got a tack, which means you're going back and forth in a zigzag pattern to get anywhere. And by the way, you're only doing that at 3 knots, so you're not going very fast. So a lot of limitations there. So another approach is to do a higher power vessel. So you can use a diesel power vehicle. I say diesel rather than gasoline. Diesel's a lot. It's cheaper. It's safer. Gasoline. You light a match and you drop it, and it's gonna singe your eyebrows if you're lucky, and if you're not, you'll die. So like gasoline, you can pretty much drop a match on it and it's going to be fine. It needs high compression to, combust. So, and then you can get kilowatts of payload power for, I said 1 to 3 for a 20-foot boat. You can do a bigger boat, you can get more power. You can have a dedicated generators and things like that on board, and you get more power. Now, the other nice thing is, if you're worried about carbon footprint, I'm putting a lot more into a smaller boat, which means I can use a smaller engine. And the reason I can achieve that density is I don't need to have a wheelhouse. There's no place on there for a person to drive. I don't need to have a head or, a toilet, right? I don't need to have the systems for that toilet, right? I don't have to have a black water system and a gray water system and a potable water system for drinking, right? I can take all of those out. That's water tanks. That's weight, and a lot of those things are, your black water system and everything. You can't necessarily discharge that depending on the waters you're in. So it means you have to keep carrying that around with you everywhere you go on a crewed vessel, right? So with all those savings, you can really ramp this down to a 50 horsepower engine to a 100 horsepower engine for a boat that would still have the full payload that's on there. So that's pretty big deal. So you still are reducing your carbon footprint significantly by switching to this, even though it's using a diesel engine. And so you're going to ask, well, what about electric and hydrogen and all this, other great stuff? And the answer for electric in particular is power, weight, and drag, right? So everything for a boat, how fast does the boat go? How long does it last? It's all down to power, weight, and drag. So if you can get the power pretty easily, you put this big, however many kilowatt propulsion system, your drag is your hull form. Well, but what about the weight? And the weight comes down to energy density, right? So this is what it translates to is how many electrons can I store? Electrons, I know it's stored chemically, but whatever. But how much power can I store in 1 pound of material on using a lithium ion battery versus how much energy is there in 1 gallon of diesel or equivalent pound of diesel, right? And the answer is there's way more in diesel. Unfortunately, that's where we are right now. Of course, battery technologies are evolving. It's getting better, and hopefully we'll achieve similar energy densities in the future that will be able to just make it all electric. And of course, we mentioned too about solar panels and stuff like that. You're only able to charge at 100 or 200 or maybe 300 watts at a time, but you put more panels on, that means more surface area, that means more weight, that means yada yada yada, right? So you get where this goes. Now it does have this is an electric ferry. That's an all electric ferry. So there is a future for this. Ferries are great because they kind of go back and forth, and they just go to one spot and they come back, and you have lots of opportunities to just keep plugging them in. Where it doesn't work great is an ocean going vessel where I've got to send it out for a really long time. So there's a place for it, and I think this will continue to grow. And what's great is that this will help mature the technology so we can put it on other boats. And then there's hydrogen, which I think will be great once we've got it. And there's not really the engines and the fuel cells and all that stuff. So I don't know if any of you are working on hydrogen fuel cells or something, but keep up the good fight. All right. So what are some of the kind of problems that need to be solved? So collision avoidance and COLREGs, which is the International Collision Regulations. So that's kind of the rules of the road for how you avoid collisions, because generally it's not enough to just avoid a collision. You also have to do it the right way. If you're driving on the road, you got to stay on the right side of the road, unless you're in one of those other countries where it's on the left. Just like that, boats have rules. This is one of those rules, hey, if you're approaching somebody head on, you both turn to starboard, you turn to the right, everybody turns to the right. That's the simplest. This is like the simplest rule, but there's a bunch of rules. But in order to do this, you've got to solve a lot of different problems. And anybody here do any kind of localization or perception, anything like that? Okay, so with perception, you've got a bunch of different sensors that are finding the contacts, right? They're finding the different other boats or obstacles that are in your way. And you want to have multiple different sensors because every sensor is bad at something, and so you know, if you've got a camera system, you know, cameras work great in the daytime. What do you do at night? Okay, well, I'll use a thermal camera at night. Well, okay, that's great. But then the range of the thermal camera is only so long because, you know, thermal cameras are really low resolution. So how do I solve that problem? And I need, you know, I need so many pixels on target in order to find it. Well, okay, well, then I'm going to use a radar. Okay, great. Well, now I've got 3 sensors and then I've got an AIS, right? So now I've got 4 sensors. So I've got to fuse all the data points together into one common picture because, you know, trust me, if you're trying to write a behavior to avoid something, you just want a map that just goes, yeah, there's a boat there, there's a boat there, there's a boat there, and I'm going to figure out how my path planning goes. You know, you're not going to want to figure out, you know, you have to correlate those somehow, right? So that's a big deal. Motion prediction is a big deal, kind of related, similar topic. And then path planning is then the next big deal. So you built your map, you know, you've figured out, you've predicted where everybody's going to drive, and then you need to plan your path to get through that crowded, congested area. And of course, you know, if you've done any path planning before, A-star, anyone done A-star, right? A-star, no? Yeah, okay, got some, yeah. So, you know, what's great about A-star is you put out this grid and you go, you know, hey, I'm just going to go from here to here to here to here, and it doesn't really care which way you're facing and whatever, right? So you got to make considerations for the fact that I can't turn around my boat on a dime, you know, at any moment, right? So you have to consider the physics of the vessel, and it's, you know, it's called these vessels are what's called non-holonomic, right? So a holonomic vessels like skid steer, you know, it turns around in place, it can do this, you know, turn on a dime, right? Non-holonomic vessel, just like your car, you turn your steering wheel, depending on how hard you turn it, it's a nonlinear system, right? It's an, you know, so that's the deal there. And then you've got long time horizons, like we talked about earlier. And then, you know, again, and then you're trying to follow COLREGs too. So it's not enough to just avoid, you also have to avoid the way you're supposed to avoid. And guess what? COLREGs is not just about avoiding stuff or driving on the right side of the road. Just like with your car, there's street signs, you know, there's lights. And, you know, you go up to a red light, you know, you don't want the autonomous car to just drive right through the light, you know, that's going to cause some problems. So COLREGs has its own equivalent things. And some of those, you know, so these are kind of all the parts, A, B, C, and D, and there's, you know, all the rules fit into these parts. And, you know, this one, you know, says, hey, you've got to treat sailboats specially because it's really hard for sailboats to maneuver. Well, so then what does that mean for you as the person who's writing the code for the autonomy for this robotic boat? Well, that means I need to know what a sailboat is. And how do you classify a sailboat? You know, so I've got to have a whole computer vision problem now of, you know, looking at camera data and going, well, that's a sailboat. And guess what? It's even worse than that, because sometimes sailboats won't be under sail. They'll drop their mainsails down and they're putting around with a diesel engine. Well, now they're a motorboat. They're different. So you have to classify those differently. So that's a problem. And then you've also got lights and shapes and sound signals. And, you know, so this is kind of a funny example, just want to show of ball, diamond, ball. That's a standard shape pattern. And I think this is limited ability to maneuver or something because they're, you know, at anchor. This is a jack-up boat, right? So you see these, they kind of go straight down and, you know, jack up into the ground, and then it doesn't move at all, right? So this thing says, I ain't moving nowhere, you know, so go around me. And then what's worse is it's right in between these, you know, these big beams. So you have to somehow identify that. And then there's these little balls here too, which say which way it's safe to go around me. Do you see those balls? Barely, right? A human barely sees them. So guess what you do? You know, if you're on a boat, you know, you get your binoculars out, you go look at it, you squint at it, you stare at it for a while, and then you call them on the radio. And you go, hey, I can't quite see what you're doing over there. I can't quite see the balls on there. And so you literally call them on your VHF radio. And you say, you know, what's your intention? Why are you moving this way? Why are you, you know, positioned like that? What's the best way to get around you? Because I can't quite tell what's going on. And they go, oh, well, you know, you got to go around this way. You know, well, what did I just run into? I ran into another problem. I've ran into a voice communication problem, right? And, you know, guess what? Voice communication is part of the COLREGs, you know, because that's a big part of navigation around in the ocean. So these are all big problems. You know, as you can imagine, I mean, you're putting Siri on a VHF radio and you're trying to, you know, drive around. Right. So, and not all of these problems are solved. So there's a lot of great future research topics in here. The other place where I think there's a lot of new work is in payload integrated autonomy. So it's what I call payload integrated autonomy. So, normally, or kind of state of the art, right, is, hey, I need to mow the lawn. So what I'm going to do is I'm just going to put a grid in place, and I'm just going to drive back and forth with no attention paid to what's below the surface, what my sensors are telling me. And of course, if you're working in different depths, your line spacing actually matters. So what do I mean by that? So again, you got a cone. You got a cone of information that you're collecting. And if the water is deeper, that cone gets bigger and bigger and bigger, which means I can see more, but it's also lower resolution, right? Because my cone is split in so many different spaces, right? And then the water gets shallower. Well, now my cone, my swath is much smaller, but I can see with really high resolution. And so then it's going to be a question of, well, what do I care about? Do I have a goal of a particular resolution? You better believe it. You've got a goal of particular resolution at a certain depth. And then the other thing is, well, maybe it gets so shallow that my line spacing was all wrong. And I've got what are called data holidays. I've got gaps in between the line. And I actually needed my line to be a little bit closer to be able to make it work, right? And you don't know that necessarily a priori, because it's, like I said, you're mapping this area maybe for the first time ever. So you may not know the depths. You kind of know typical depths, but not exactly what it is. So it's really good idea then to integrate that payload data into the navigation system and adjust your line spacing. And so you can see this is some work from University of New Hampshire, and they were using a boat that I had worked on, and they made up a new algorithm to change their line spacing dynamically based on the depth. And you can see they can really get all that resolution and detail in, where you wouldn't have if you just left it alone, right? So you could do some cool stuff. And that means you can either get better science or you can optimize your driving. Because maybe I can drive a little more efficiently because I don't have to drive back to cover an area that I missed before. All good stuff. And then it's always good to talk about the boring stuff, regulatory challenges, the bureaucracy. We're all faced with it. We all have to meet it at some point. And I will say it's really behind. It's really, really behind for boats. One of the great things about cars is that you go to a given country and guess what? There's a highway, traffic safety administration, and it's only bound to, the United States, and, we can make a decision in the United States and it doesn't really affect anybody else because our roads don't affect other people's roads, right? Not so in the marine industry, because you're literally dealing with international waters and international borders. So all of that goes back to IMO, your International Maritime Organization, who they kind of help make the rules. But they're really slow because, guess what? How long does it take to make a UN resolution pass? I don't know. No one knows. It takes forever, right? Coordinating all these different countries together. And then guess what? That means that our own society, our own administration and Coast Guard rules and everything like that, we lag behind because we don't want to get involved. We're going to wait for the IMO to make a decision on these things before we do anything about it. So they just stay out of it. So the Coast Guard doesn't really make any rules. And so guess what? There's very few rules. There's guidance, but there's not a whole lot of rules. And then there's also other things that are involved in boating, which is the class societies. And the class societies are what help you get insurance. They, they actually inspect the vessels and they make sure that they're, whatever. So there's all kinds of rules that they make up. Like the American Bureau of Shipping and Lloyd's of London and, Der Nords Veritas, Norway, right? So they're all kind of lagging behind. So a lot of times we just call it deployed equipment. It's just stuff we're throwing out, just like a buoy, even though it moves around and it drives itself and it could potentially crash into somebody. It's just considered like a buoy, go figure, right? So we have to do, as an industry, we've got a lot of responsibility, to safety and really to not be the ones that screw up and cause a lot of harm, right? You know, we don't want to hurt anybody, so safety is a big priority for us. But it's even kind of more risky for a business because the regulatory environment isn't established, right? So big thing. And then the other thing I want to touch on is the ITAR, which this drives me crazy, so I'm more just complaining about it. So there's an international traffic and arms regulations, and ITAR regulates things like nuclear weapons and missiles and stuff like that, which makes sense. Hey, we shouldn't export our nuclear weapon technology to other countries. Makes sense. And unfortunately, for some reason, our past administration decided that COLREGs compliant collision avoidance systems should be regulated by ITAR. And so, well, that sucks. That means that I can't export, without getting a special license to export my, COLREGs compliant navigation autonomy, which, by the way, by nature of a boat, you're driving the boat around, you're exporting it all the time. You cross into international waters, that's an export, so you have to have a license to export that. And it's also really unfortunate because it restricts who can work on it. It restricts our hiring to only US persons. So it really restricts innovation. Anyway, call your congressman and tell him to take collision avoidance technology off of the munitions list. I would really appreciate it. We would all appreciate it. So anyway, let's talk about careers though. Interdisciplinary knowledge is very key. So you see, we hire every kind of engineer. Are you an engineer? Yeah, we need that kind of engineer. And all kinds of cool topics, right? Everything: data fusion, information theory, control theory, computer vision, deep learning, microservice architectures, modeling and simulation, industrial control panels and communication protocols. So all this stuff that you cover, remember, highly integrated systems. You got all these mechanical systems that are being brought together, and they all have to go into a single computer system that's managing that. It just means that you need to know a lot of things, especially, for smaller companies. You got to kind of, be able to wear a lot of hats and know a lot of different things. Some great reads if you're interested in learning more about this kind of stuff. I'd always refer. So Dr. Sebastian Thrun has a great book, Probabilistic Robotics. He's also a guy, he started Udacity, so that's why there's like all the self-driving car things on Udacity or whatever. So there's a lot of free resources that you can get that he's kind of started. Great stuff, mostly related to cars, but a lot of it's transferable. Fossen is like the guy for marine control systems, so if you want to learn about, how do you control a boat, Dubin's curves and all that kind of stuff, he's the one. And then Mike Benjamin over at MIT has done a lot of autonomy behavior kind of research. And then this is also where ITAR gets really funny and silly because they don't regulate it when it comes to educational applications, but for commercial it is regulated. So you've got MIT's over there, and they've got open source solutions for COLREGs compliant autonomy, COLREGs compliant asterisk autonomy, some of the rules, and they can export that all over the world. It's open source, but commercial company can't. Go figure. So anyway, and we're hiring. So if our shameless plug. So if you're interested in a career in marine autonomy, like I said, we're located right in town. Happy to hear from you. So I think that's all I got.